All right, good morning. We are working on section 3.1. Inverses. Okay. Section 3.1, inverse functions rather. Inverse functions. Inverse functions. So make sure you are reading your text. It's very important that you read your text, okay? So an inverse function is exactly what it sounds like. An inverse function will undo what an original function did. So for example, if I have f of x equals 2x plus 1, okay? That function, x is your input, so we'll put an x value in there and then the function will operate on it, and then we will get a y value out, right? So for example, f of 2, let's do f of 3 maybe. F of 3, when I put x equals 3 as my input into the function, it'll multiply this thing by 3, then it'll add 1. 2 times 3 is 6, 6 plus 1 is 7. So this function takes as input, functions can be thought about as input-output machines. The input is x equals 3, and the output for this function is y equals 7, okay? We'll input x equals 3, and we'll get as output y equals 7. So every function does something different. Functions are rules. They are input-output machines. You'll put a value of x into the function, and you'll get a certain value of x out of the function, or a certain value of y out of the function. So when we talk about an inverse function, if I said that g of x is the inverse of f of x, okay, then g of x is going to undo what this function does. So I need g of 7 to give me 3. Because if f took 3 and gave me 7, then g will do the opposite. It'll take the 7 and it'll give me 3. It'll undo what this original function did. That's what inverse functions do. Now, let's look at this one. When you look at simple basic functions, you can actually probably tell what the inverse function needs to be, okay? So this function, when I take some x and I put it into this function, the first thing it does is it multiplies by 2, then it adds 1. It multiplies it by 2, then it adds 1, okay? So the inverse function, how should I write it? Well, g of x is going to do the opposite. So again, the first thing the function did was multiply by 2, then it added 1. So g of x is going to take x, whatever you put in, it's going to subtract 1 first, then it'll divide by 2, okay? That'll be the inverse of this function. That's the opposite process. If this one multiplies by 2 first, then adds 1, this one should subtract 1 to undo this part, then it'll divide by 2 to undo this part. So that would be the inverse function g of x. And I can check myself. Let's take g of 7. G of 7. Where I had an x, I put a 7. Okay? Well, 7 minus 1 equals 6 over 2, which is 3. So I do see that g of 7 gives me 3. So g of x is the inverse of f of x. This is how inverse functions work. Now, I just wanted to make sure I showed you what an inverse was, all right? Now we know what inverse functions are, we know how they operate. Now we will not always be able to tell what the inverse is just from the original function, okay? We're gonna have a process by the time it's all over. We're gonna have a process that helps us determine what that inverse is, okay? So read this stuff. The first thing we need to know is all functions don't have inverses. All functions don't have inverses. Only one-to-one functions have inverses. Only, I'm gonna write 1, 2, 1. And you're gonna see me write shorthand like that, one-to-one like that. Only one-to-one functions have inverses. Only one-to-one functions have inverses. So the definition of one-to-one, it's on page 357. The definition of being one-to-one is on page 357. Pretty straightforward though. One-to-one says, if A equals B, then F of A equals F of B, and if F of A equals F of B, then A equals B. So either way I look at it, it has to work both ways. If I have, and these A's and B's are like X coordinates, the F of A's is like a Y coordinate, right? So one X coordinate is equal to another, then corresponding Y coordinates will be equal. Or if I knew the two Y coordinates were equal, then those corresponding X coordinates would be equal, okay? And this is if I have just the definition of a function. There's also something called the horizontal line test. For one-to-one. And it says, if any horizontal line drawn through a function intersects the function more than once, it is not one-to-one. So if I've got a graph, it's really, really easy to tell if a function is one-to-one, okay? If I have a graph, it's really, really easy to tell if a function is one-to-one. And remember, we had the vertical line test to tell if a function was to see if a relation was a function, a vertical line test. Now we've got the horizontal line test to tell if a function is a one-to-one function. And again, the reason we need to know this is because only one-to-one functions will have inverses. Okay, only one-to-one functions will have inverses. So with this in mind, example one. Are the functions one-to-one? Okay, example one, are the functions one-to-one? Okay, well, the first function they give me, A, F, equals, so the ordered pair is 1, 4, they give me 2, 3, and they give me -2, 4. So that's my function. And I want to know, is this thing one-to-one? So I'm using this definition. So either whenever two x coordinates are equal, then the corresponding y coordinates better be equal, or if two y coordinates are equal, then they better have the same x coordinate. But I see right here from this point and this point, I've got two y coordinates that are the same, the 4 is the same, but the x coordinates are different. So this thing is not. It is not one-to-one. Now, if you remember when I wanted to know if something was a function or not, the definition of a function said that whenever, well, we had a couple of definitions. If I had a function, we said that if I had it in these ordered pairs, I said that I couldn't have any repetition in the x coordinates, in that first coordinate. So the one-to-oneness, I see that if I have a function defined by these sets of ordered pairs, if I have repetition in the y coordinate, then it's not a one-to-one function. So again, when we had a definition of a function, for every element, the definition, the official definition was for every element in the domain, there's exactly one element in the range. And again, if I had it in these ordered pairs, what that meant was I couldn't have repetition in the x coordinate. So now for this one-to-oneness, if I have it in ordered pairs, if I have repetition in the y coordinate, it is not a one-to-one function. B. 1, negative 1, and 2, 0. Well, this time I do not have repetition in my y coordinate. Right? So for every different y coordinate, there's a different x coordinate. This is a one-to-one function. So one-to-one, this is pretty easy to tell. Pretty easy to tell. If I've got ordered pairs, all I have to do is look and see if I have repetition in my y coordinate. If I do, it's not a one-to-one function. Okay. Example 2. What about this horizontal line test? That's even easier. Are they one-to-one? So they're going to give me 3 basic graphs. A, x and y. They give me something like that. Okay. Is this a one-to-one function? Okay. Well, I can draw any horizontal line I want to draw anywhere in the plane. And if I happen to draw it maybe here, I see that it intersects it once, twice, 3 times. This is not one-to-one. Because I found a horizontal line that hits it more than once. B, x and y. B says, there's my function. Both of these are functions. They pass the vertical line test, so they are functions. And now any horizontal line I want to draw anywhere in the plane, doesn't matter, it'll hit it only one time. So this is a one-to-one function. Okay? And finally, C. C, I have this graph that does this. There's my x-axis and my y-axis. Well, any horizontal line will hit it only once. Okay? This is a one-to-one relation. Now, if you did any horizontal line, hits it one time, right? But if you did a vertical line, it would hit it once, twice. This one is not a function. It is one-to-one, but it is not a function. Okay? It is one-to-one, but it is not a function. All right. Well, the third possibility is, so now we know how to figure out if something is one-to-one when I'm giving that thing the function in ordered pairs. The function is defined via ordered pairs. Now I know how to determine if it's one-to-one via the graph, right? So the last question is, how do I know if I'm given an equation if it's one-to-one? So that's what example 3 looks at. So I'm just going to say example 3. Are these one-to-one? So this time they're going to give me an equation. So f of x equals 2x minus 3. It's in function notation, so it is a function. But I want to know, is it a one-to-one function? F of x equals 2x minus 3. So let's remember our definition. Whenever the x coordinates are the same, the y coordinates should be the same, or vice versa. Whenever the y coordinates are the same, the x coordinates should be the same. That's what it means to be one-to-one. Okay? So let's just think about this thing. When I look at maybe a particular x equals 5. Okay? When x equals 5, if I put a 5 here, I get 2 times 5, 10, minus 3. So y equals 7. 10 minus 3 is 7, I'm sorry. Y equals 7 would be what I get out of that function. And the question is, y equals 7 corresponds to x equals 5. Is there any other value of x that I can put into this function to get y equals 7? And the answer is no. Now the other way you can think about this is, if you knew this thing is a graph of a line, 1, 2, 3, negative 3, 2/3, 2, 1. The graph of y, f of x equals 2x minus 3 looks like that, okay? So I can actually apply the horizontal line test and see that it's one-to-one also. But just from an analysis, X equals 5, plug it into here, I get y equals 7. So for that y coordinate, that is the only value of x that will give me y equals 7. So for every different y coordinate, I'm going to have a different x coordinate. That's what it means to be 1 to 1. So that one is 1 to 1. That one is 1 to 1. B, f of x equals x squared plus 1. Okay? And I do the same type of analysis. Let's say x equals 1. When x equals 1, 1 squared plus 1 means that y equals 2. And again, I ask myself, is there any other way that I can get y equals 2? Okay? And actually there is, when x equals negative 1. When x equals negative 1, if I plug the negative 1 in, I'll have negative 1 squared plus 1. Negative 1 squared is positive 1. 1 plus 1 makes 2. So I see when x is positive 1, I get 2, but when x is negative 1, I get 2 also. So there's one value of y that has more than one value of x that corresponds to it. This is not 1 to 1. That function would not be 1 to 1. For every value of y, there has to be only one value of x that corresponds to it. Okay? So this thing would not be 1 to 1. So now we know how to tell when functions are 1 to 1. Now we know how to tell when functions are 1 to 1. Okay? So, the next thing we want to make sure, we're going to get to the point where we have, again, a process to find these inverse functions, but we got to get some background first. So now we know how to tell which functions will have inverses, because again, only 1 to 1 functions are going to have inverses. That's what it's going to turn out to be. Only 1 to 1 functions will have inverses. So next we want to determine whether two functions are inverses of each other. Next, we want to determine when two functions are inverses of each other. So here it is. This is our process, that f g of x. Well, let's let f of x be 1 to 1. So, if f composed with g of x equals x, and g composed with f of x equals x, then f and g are inverses of each other. Okay? So I'm starting out with 1 to 1 function. F and g are 1 to 1. They both have to be 1 to 1. If f composed with g, composition of functions, hopefully you remember that. We did that earlier in the semester. If both f composed with g of x equals x and g composed with f of x equals x, then two functions are inverses of each other. And note, we will use this notation to represent the inverse of function. Okay? So when you say f inverse of x, that's the inverse function. Okay? That does not mean f to the negative 1 power, right? That's not, I can't say that f inverse of x is 1 over f of x. That's not the exponential notation. This is just how I write the inverse function. So now, with this in mind, this statement becomes f inverse composed, f inverse composed with f of x equals x, and the opposite direction would be f composed with f inverse of x equals x. So I'm just rewriting these two statements, this and this. Now that I know, instead of saying g of x is the inverse of f, I'm going to call my inverse f inverse of x. So this statement and this statement become this and this when I use my inverse function notation. Okay? So with that in mind, example 4. Are these inverses of each other? So A, they give me f of x equals 100 plus 12x. And g of x equals x minus 100 over 12. Okay, they give me those two functions, and they want to know, are these two things inverses of each other? Okay, well, let's use our test. I need to compose f composed with g of x and see if I get x. Then I'll do the opposite, g composed with f of x and see if I get x. So let's do f composed with g of x. That means f of g of x. That's how I define the composition of two functions. Now plug in what g of x is. G of x is x minus 100 over 12. So that means in the function f of x is this stuff. So where I used to see an x in the function f, I'm going to put all of this stuff. Everywhere I used to have an x, I'm going to put all of that stuff. So 100 plus 12 times x, but x is x minus 100 over 12. Well, these 12s cancel. So I get 100 plus x minus 100. These two things, 100 minus 100, cancel. And so I get x. So far I got half of it done. F composed with g of x is x. But again, it can't be just one direction. It has to be both statements. You've got to do the composition the first way, like we just did, f composed with g of x and get x, and you've got to do the other. You've got to do both. If they both are x, then they're inverses. If one is x and the other one is not, they're not inverses. Okay? So now I got to do g composed with f of x. Well, again, the definition of composition of functions says that. Now I plug in f of x. F of x is 100 plus 12x. So now everywhere in the function g that I used to have x, everywhere in the function g that I used to have just x, I'm going to replace just x with all of that stuff. So g of x was x, so in place of x I'll put 100 plus 12x. So in place of x I put all that stuff minus 100. Minus 100 all over 12. Okay? And the parentheses aren't really doing anything, so I didn't have to write them, but I wanted to make sure we understood the process. So 100 minus 100, they cancel. So 12x over 12, but that's just x. So I've shown that f composed with g of x is x over there. Then I showed up here that g composed with f of x equals x. So since they're both x, then these two things are inverses of each other. Hence, f of x and g of x are inverses of each other. B, they give me the two functions. H of x is the cube root of x minus 1. And they give me the function k of x equals negative 1. They say plus x cubed. Okay? So again, I've got to do both compositions. I've got to do h composed with k of x. That means h of k of x. Plug in k of x. K of x is this stuff. So now everywhere in the function h that I used to have an x, I'm going to put all that stuff. So cube root. And instead of just x, I'm going to write all that stuff. Negative 1 plus x cubed, okay? And then I'll have the minus 1 stuff still. So there's h of k of x. Now, I can simplify this a little bit. Negative 1 minus 1 cube root x cubed minus 2. Okay? But this stuff under that radical, the only way that I can get rid of that cube root is if this stuff were a perfect cube. Okay? But the problem is that stuff is not a perfect cube. So I can't simplify this. I will not get x. So I don't even have to do the k composed with x, the k composed with h of x, the opposite direction. Because the moment you don't get x in either direction, you're done. They are not inverses. They are not inverses of each other. You can do the other direction if you like. I don't think that one will work out either. But again, to be inverses, both directions have to work out. So since I don't get an inverse, so since I don't get x for that direction, I don't have to do the other direction. They won't be inverses of each other. Okay? All right, so now we finally are at the point where we have enough information. Now we can actually find the inverse of a function. Find the inverse of a given function. With it, we have enough information. We know when a function has an inverse. Only one-to-one functions have inverses, so I know how to determine that. We know when two functions are inverses of each other. We just did that. They're only inverses of each other if f composed with g of x equals x and g composed with f of x equals x. Now we're at the point where we can actually figure out what our process is to find an inverse for given functions. So this is our process. This is on page 360. Okay? Page 360, really important. This is our process or procedure. So, step one. You got to start with a one-to-one function. We already said that. I'm not going to write that, read it. So, step one, replace f of x with y. Replace f of x with y. Step two, interchange x and y. So where I used to have a y, I'm going to replace it with x. Where I used to have an x, I'm going to replace it with y. I'm going to interchange the x and y. Next, I'm going to solve for y. And I'm going to say, well, I'm not even going to say, just solve for y. Okay? And step four, if I can solve for y, I found my inverse, and I'll replace y with my inverse notation, f inverse of x. Okay? There's my process. This is how I find an inverse function. Given a function, I can use this four-step process to find an inverse function. I will replace f of x with y, step one. I will interchange the x and the y, step two. Then I'll solve for y, step three. And after I've solved for y, the moment you solve for y, you have your inverse function. The last step is just to write it with that inverse function notation. So I'll replace y with f inverse of x. Okay? All right, so let's do one. Example 5. Example 5, this is on page 360. Write an equation for the inverse function. Write an equation for the inverse function. Okay? And they give me f of x equals 3x minus 1. Okay? So, step one, replace f of x with y. Step one. Step two, interchange the x and the y. So where I had a y, put an x. Where I have an x, put a y. Interchange the x and the y. Okay? Step 3, solve for y. So let's add 1 to both sides. I added 1 to both sides. If I add 1 over here, I get x plus 1. If I add a 1 over here, negative 1 plus 1 makes just 3y left over. I added 1 to both sides. Okay? I'm solving for y, so to get the y by itself, the next step would be to, and if you want to write that plus 1, I can write it like that. Okay? I added 1 to both sides. So now the last step to solve for y, to get the y by itself, would be to divide by 3. But if I divide by 3, whatever you do on one side of the equation, you have to do on the other. And I'm going to turn it around, because these 3's cancel. And you'll get y equals x plus 1 over 3. And step 4 says replace y with f inverse of x, because you found your inverse. There's my inverse function. Okay? There's my inverse function. All right? Well, that's the inverse. And again, for these basic simple functions, you can almost tell this original function, whatever x you put in, it first multiplied by 3, then it subtracted 1. So the first operation when you put an x in, when you input x equals whatever, it multiplies by 3, then it subtracts 1. So the inverse function is the reverse of that. So when you put an x in now, the first thing it's going to do is add 1, then it's going to divide by 3. That is the exact opposite process of the original function. Okay? Well, let's check it though. Let's check it. Let's check it. So we're going to do f inverse composed with f of x. So that means f inverse of f of x, that's 3x minus 1. So now I put 3x minus 1 into here, so there's f inverse of x. Everywhere I used to have an x, I'm going to put that whole 3x minus 1. So x plus 1 becomes 3x minus 1 plus 1 all over 3. Okay? But 3x minus 1 plus 1, the minus 1 and the plus 1 kill each other. You get 3x over 3, you get x. Well, that's f inverse composed with f of x, you get x. Let's do the opposite direction now. Let's do f composed with f inverse of x. Well, the definition of composition of functions says that that's that. So f inverse of x was this thing. So that means f of x plus 1 over 3. Right? So this means f of this stuff means in the original function f, where I used to have an x, I'm going to put all that stuff. So f used to be 3 times x minus 1. But where I used to have x, I'm going to put all of it. So 3 times, I used to have an x, but now I'm evaluating here, so I put all of that. And then minus 1. Well, the 3's cancel. I get x plus 1 minus 1. That's x. So f inverse composed with f of x is x, and f composed with f inverse of x equals x. So since both are satisfied, we've verified that these two things are inverses of each other. Okay? That's how you find an inverse function. And again, with these basic functions, you can literally look at the equation of the function and kind of tell if it's going to be, if the inverse function will work. Now, when we get to more complicated functions, you will not be able to do that. Okay? When we get to more complicated functions, you will not be able to do that. Okay? All right. Now, let's do example 6. Find the inverse function. So the function they give me is f of x equals 3 minus x. Divided by x plus 3. 3 minus x divided by x plus 3, okay? Now this again is one of those that, again, it's not quite as obvious how you find the, or that you can tell, like literally here we can tell. This function took, right here, when you plugged in an x, it multiplied by 3, then subtracted 1. So the opposite of that would be to add 1 first, then divide by 3. That was not as clear anymore in terms of just a quick analysis of the function, determining what the inverse would be. The moment I looked at that function, I could figure out what the inverse is. When I look at that one, it's not as obvious what the inverse is. So that process will not always work, okay? But thank goodness we have our 4-step process that always does work, okay? Step 1, write y equals 3 minus x over x plus 3. Interchange x and y. Interchange x and y, that was step 2. Now I need to solve for y. Well, first I get rid of fractions, so I'm going to multiply both sides by y plus 3. I need to get rid of fractions. Get rid of fractions, multiply by your LCD. So I'm going to multiply this side by the y plus 3, and this side by the y plus 3. And on this side, they cancel. So over here, x times y is xy, x times 3 is plus 3x. And on this side, again, these two things cancel, and I'm left with that. Okay? I got rid of fractions. Okay? Well, now I'm solving for y. Remember what I'm after. I'm trying to solve for y. So we got to get all the y terms on one side and all the other terms on the other side. So I'm going to add y to both sides. If I add y there, I'm going to add y here. Okay, so I get xy plus y, and the 3x is still there, equals. On this side, these two things cancel, so I just have the 3. So I got all the terms that have a y on the left side of the equal sign, and hence I need any term that doesn't have a y on the other side, so I'm going to subtract 3x from both sides. If I do it there, I got to do it there. Okay? Getting closer. I got all the terms with y on one side, all the terms that don't have a y on the other side. Now, there's a y in this term and this term. Let's pull it out. I can factor it out, right? Y times x is xy. Y times 1 is y. So I factored it out. Okay? Well, I'm solving for y, so this stuff is multiplied by y. To get rid of something that's multiplied by what we want, we divide by that thing. If I do it over there, I got to do it over there. Whatever you do to one side of the equation, you do the exact same thing to the other to keep it balanced. Well, x plus 1 over x plus 1 cancels. Anything divided by itself is 1. X plus 1 over x plus 1 is 1. So I'm left with y equals 3 minus 3x over x plus 1. So I've solved for y. The last step is to write my inverse notation. There's my inverse function. There's my inverse function. All right. So it turns out, again, that 4-step process, that's how we're going to find inverses. That 4-step process. If you wanted to check that one, you could. F composed with F inverse of x equals x, and F inverse composed with F of x equals x. It works, okay? There's one thing I did not mention that I do want to mention. That's something about the graphs of a function and its inverse. Okay? There's something about the graph of a function and its inverse. Graph of a function and its inverse. Okay? X, y. Let's look at this function we looked at, example 5. Y equals 3x minus 1. Okay? Let's graph it. Y equals 3x minus 1. When x is 0, this goes away. Y is negative 1. So 0, negative 1. Now I'm gonna use the slope, mx plus b, right? The slope is 3, so I go up 3 over 1. So this line looks just like this. This is y equals 3x minus 1. You could have got this line by doing a t-chart, x and y, right? And I said when x is 0, 3 times 0 is 0 minus 1, y is negative 1. That's this point. Then when x is 1, put a 1 in. 3 times 1 is 3, 3 minus 1 is 2. So 1, 2, that's how I got that point. So there's that line, okay? The inverse function was y equals x plus 1 over 3. The inverse function was y equals x plus 1 over 3. Okay? Well, let's do a t-chart for this line. And since I got fractions, I'm going to be careful in how I choose my x values, just to avoid fractions, because you guys hate fractions, okay? So I'm going to say when x is 2, okay? Plug a 2 in here. 2 plus 1 over 3 is 3 over 3, or 1. So 2 comma 1 is on that line. So 2, 1. That's the point on my line, okay? Let's do another one. Let's say when x is negative 4. Okay, negative 4. Put a negative 4 where the x is. Negative 4 plus 1 over 3. That's negative 3 over 3. That's negative 1. Okay? So negative 4, negative 1. So this line right there is there. Okay? Well, y equals x. This is the line y equals x, right? 1 comma 1 is on y equals x. The x and y coordinate equal. 2 comma 2 is on that line. Negative 1 will be on that line, etc. Actually, it should come through the origin. Because 0, 0 will be on that line. And this is in the book on page, this is in the book on page 361. You can see this graph in the left margin. Well, it turns out the graph of a function is inverse. Whatever the original function is, the other function will be the reflection of that graph across the line y equals x. That's how inverse functions are related. One graph is the graph of the other. If you take the first graph of the function f, for example, flip it across the line y equals x. So if I take this line and flip across this dotted line, I get exactly that line. That's how inverse functions are related graphically. One function is the reflection of the other across the line y equals x when those two functions are inverses. So that's a property that all inverse functions have. Okay? You can take a look at that on page 361. Okay? Well, example 7, they talk about finding an equation of an inverse function. I'm not going to do that, but I want to set it up for you because there's one thing we have to be a little careful on with that one. Okay. So example 7. They say m of x, given m of x, equals, they say x squared plus 4. But they give me a restriction. They say for x greater than 0. For x greater than or equal to 0. That function is only defined for x greater than or equal to 0. They say find the inverse. Now, what I want to make sure we understand, that function is written, if I didn't have this restriction, that function is not 1-to-1. Y equals x squared plus 4 is not 1-to-1. You can look at the graph if you wanted to. Y equals x squared plus 4, that's the x and that's the y axis. 1, 2, 3, 4. It looks like this. There's y equals x squared plus 4, without a restriction. This is for all x. This is without that restriction. So it would not pass the horizontal line test. So it is not 1 to 1. But with that restriction, they say only for x bigger than or equal to 0. So if you're looking at this thing only for x bigger than or equal to 0, it's really just this piece. So now it is 1 to 1, and now I can find an inverse function. So that's why they gave me that restriction. Because the original function without the restriction is not 1 to 1, hence it does not have an inverse. Okay? So when you find this inverse, and I'll let you look at it, okay? And again, that's the problem for these functions that are not 1 to 1. Well, take a look at it. If you have any questions about it, reach back out to me and I'll be glad to work it out for you. But I want you to look at that one and think about it. But that's why they gave you that restriction. Okay? That's why they gave you that restriction. Okay? Let's see. And example 8 is pretty much the same stuff. I'll let you do that. Again, I don't think there's anything particularly difficult in example 7 or 8. That 4-step process won't change. That's how you find inverses. Number 1, write y instead of f of x. Step 2, interchange x and y. Step 3, solve for y. Step 4, write the function inverse notation. Replace y with f inverse of x. That concludes 3.1. We're in 3.2, exponential functions. This is section 3.2, exponential functions. And you know what, I think I want to break these videos up. So this concludes this video.